All right, so today we're going to look at proving limits of functions involving square roots. Okay. So here's a typical example you might see. Suppose we want to prove that the limit as x approaches, say 4, of the square root of x equals 2. Let's say we want to prove this formally using epsilon-delta. Proof: let epsilon greater than 0 be given, and let delta equal something. Let x satisfy 0 less than x minus 4 less than delta. Okay? Then what's going to happen? Well, we start off in the usual way, square root x minus 2. We want to show that this can be made less than epsilon. Now, this does not factor. So this is a bit different than what we're used to with polynomials. Okay? We want to get an x minus 4 in the picture because we know something about that. We know that's less than delta. So we have to mess around with this and get that x minus 4 to pop out. What should we do here? Well, we have a square root of x minus square root of 4. So a good place to start would be to rationalize this. Okay? So let's multiply and divide by the same thing, root x plus 2. Okay? So this equals root x minus 2 times root x plus 2 in abs values divided by root x plus 2 in abs values. Okay? So we're multiplying the top and the bottom by the same thing. We're not changing anything. And the top now will become root x squared minus 2 squared, which is x minus 4 in abs values. Okay? Alright, so this is looking good. We know that the top, the numerator, is less than delta. We want to replace the denominator with a constant. Okay? We don't want this variable x to be. Well, the first thing actually that we can do is drop the absolute value, because look, we don't even need it. 2 plus root x is always positive, since root x is always positive. Okay? So actually, at this point, we can say that this is equal to x minus 4 over 2 plus root x. Now, root x is always positive. That means it's always greater than or equal to 0. So 2 plus root x is always greater than or equal to 2. Notice that the smallest the denominator can be is 2. Which means that this entire fraction is less than x minus 4 over 2. Actually less than or equal to. Okay? We've taken the denominator and replaced it with something smaller. That makes the entire fraction bigger. Okay? So this is looking good. This is less than or equal to x minus 4 divided by 2, and now we have just delta and constants. Okay? So we can replace the numerator now with delta. So we have delta over 2, and now we can set that business equal to epsilon. So what does delta have to be? 2 times epsilon. So this is equal to 2 times epsilon over 2, which is epsilon. Proof is done. And what must our delta be? 2 epsilon. Now, there is a very, very subtle point to be made over here. If our epsilon happens to be very big, then our delta, 2 times epsilon, will also be big. Perhaps even bigger than 2. Now, that's a no-no, because look what we have here. X minus 4 has to be smaller than delta. Sorry, when I said 2 previously, I actually meant 4. All right? We could have delta being bigger than 4, and that can't happen, because if x minus 4 is less than, let's say, 5, then that's telling us that x might be less than 0. If x is taken from within this window, x might be less than 0, and then root x won't be defined. So in this situation, we have to pay attention to how far away our point is from the edge of where the function is defined. We have to make sure that these x's, f is going to be defined at them, okay? So square root function looks like this, and the function simply is not defined to the left of 0, all right? So if we're considering the point at 4, the biggest that our delta window can be is a size 4. We can go all the way up to 0 with our delta window, but we can't go past here. Otherwise, we'll have a problem. Not every x from the window can even be plugged into the function. So because of this domain issue, we do need a minimum in here. So I'm just going to make that correction real quick. Delta has to be equal to the minimum of, in this case, 4 and 2 epsilon. Okay? So similar type of problem as we had to confront before when we were looking at quotients. Okay? We couldn't encompass the asymptote in our delta window because the function wouldn't be defined at the asymptote. Okay? Here we can't stray outside of the domain of the function. That's true in general. With polynomials we didn't have to worry about this because the domain of every polynomial is just R. Okay? Here we do have a restriction. So we have to make sure, although it might not be entirely necessary. I mean, you could get away with maybe saying that delta is 2 epsilon, you know, at school and nobody would really notice. But if you really want it to be formal and give a rigorous proof, then you do have to pay attention to where the function is defined, okay? So in this case, since we've made that change, we introduced the minimum. What happens is this. There we go. Now the proof is done. All right, so let's do a slightly more involved example. Okay? We're going to do the limit as x approaches -2. I put that negative in there for kicks, because so far every example we did involved a positive number being approached. This time we're going to explicitly put in a negative number. X is approaching -2, and the function is root x squared plus 5. Okay? And if you think about it, you plug that -2 in there, it gets squared to make a 4. 4 and 5 under the root gives us root 9, which is 3. Okay? So the limit is correct. The 3 lines are there. All right? Let's begin the proof. So first of all, because of this subtlety that we had last time, you might think you'd need a minimum over here. Actually, if you think about it, root x squared plus 5 is defined everywhere. The domain here is all of R, so we actually don't need to worry about that. Okay? Not in this example. That's why it's good to have sort of a rough idea of what functions look like. Okay? What does root x squared plus 5 look like? Well, you can always use Wolfram Alpha to graph it, but it's helpful to know roughly what you have here. So the smallest that this function can be would be root 5. Okay? That's if x is equal to 0, so say there's root 5, 2.3 roughly, 2.2. And then as x gets larger in both directions, this function approaches root x squared, which is root x. So far off, we should have something that looks like an absolute value, and the function is even. So that tells us that the function will look something like that. And these lines here are going to approach x. Okay? There we go. So that's just a rough visualization of what's going on. Okay? These are slope 1. Okay? All right. So x is satisfying this inequality. All right? I plugged in the -2 in here, so this will be an x plus 2 when you, the negatives will cancel. Okay? So let's begin the proof, and we're going to try to look for the x plus 2 this time. So, root x squared plus 5 minus 3 in absolute values. We're going to do the same thing as we did before. We're going to multiply by the conjugate here to rationalize the numerator. That's the only way to really get rid of the square root, which is what we want to do because we want to bring this in, and this has no square root. So, root x squared plus 5 minus 3, that's going to equal root x squared plus 5 minus 3 times root x squared plus 5 plus 3 over root x squared plus 5 plus 3. Now the benefit of doing these square root questions and multiplying through by the conjugate like this is that the object you get in the denominator is always positive, so you never need the absolute value really, okay? So we can drop the absolute value here. So this is going to be equal to, that multiplies out to be x squared plus 5 minus 9. And in the bottom we're just going to have a root x squared plus 5 plus 3. And now the top is going to be x squared minus 4, so that's going to factor into x minus 2 and x plus 2. Okay, so this is going to be equal to x minus 2, x plus 2 over x squared plus 5 plus 3. All right, now the x plus 2 is the quantity in this case that's less than delta, and we want to say something about x minus 2, the size of it. So this is where our stipulating comes in, okay? So stipulate, the delta is, what value do we want? How about 3? I could use 1, but why not use 3 for fun? Stipulate the delta is less than or equal to 3, okay? Just to show you that it really doesn't matter what you do when you're stipulating here, okay? At least in this case, since we don't have a domain problem anywhere, all right? So we're stipulating that delta is less than or equal to 3. That tells us that x plus 2 is less than 3, okay? Now we want to say something about x minus 2. So the usual trick can be used. X minus 2 is equal to x minus, or rather x plus 2 minus 4, which is less than or equal to x plus 2 in Ab's values, plus 4, which is less than 7, because we have 3 plus 4. Okay, that's 7. Okay? All right, so we're going to replace that quantity by 7. What should we replace the denominator by? Well, there are many things. X squared is always bigger than 0, so we could forget about the x squared entirely and have 7 divided by root 5 plus 3. That doesn't look as nice because we still do have a square root. So we can drop the entire root part and have 7 over 3 here. We could also drop everything and just replace the denominator with a 1. 3 plus root x squared plus 5 is always bigger than 1, as you can see from the graph. Just add 3 to it, always bigger than 1. So we could do that. Okay. So there are many options available. So let's put in the 7 first. So this is less than 7 times x plus 2 divided by, and now the denominator could be 3, it could be 1. I'm going to say, let's just make it 1. Okay? So this is less than 7 over 1 times x plus 2, and now x plus 2 has to be made less than 7 over epsilon. So this will be less than or equal to 7 times 7 over epsilon over 7. Whoopsie. Now the 7's cancel out and we get epsilon. Okay? So the delta is going to be a minimum of 3 and epsilon over 7. Okay? 3 and epsilon over 7. There we go. And that's the end of the proof. Alright, so for our last example, we're going to prove that the limit as x approaches 8 of this crazy function, x to the 2/3, equals 4. It's good to have an idea of what x to the 2/3 looks like. So, what does it look like? Well, we know what x to the 1/3 looks like. That's just our cube root function, which looks like this. It's like our x cubed function reflected in the line y equals x. So there's the cube root. Now when you square the cube root, what happens? The positive arm starts increasing faster, and the negative arm gets squared into a positive and increases at the same rate as this side. So we have something like this. Okay. We see that there is no domain problem here. There's a differentiability problem at 0, but more on that later. There's no domain problem. Okay? So let's go through the proof. We'll begin with x to the 2/3 minus 4. And we want to mess around with this, and hopefully somewhere along the way an x minus 8 is going to pop up. And we can bound that by delta and bound the rest of the junk that we get along the way with a constant. And now we're looking at this and we're stuck. How do you rationalize this? Or what is the conjugate that we have to multiply by? Well, in this case, we don't have a square root. We have a cube root, right? X to the 2/3 is x squared under a cube root. Okay? So we do have to multiply by the conjugate of a difference of cubes, or rather a difference of cube roots in this case. Okay? We have the cube root of x squared minus, and then 4 can be written as a cube root as well. Okay? It's the cube root of 64. So how do you multiply by the conjugate here? Well, it helps if you remember how to factor a difference of cubes. So if we want to factor something like a cubed minus b cubed, let's forget about the absolute value actually. Say we want to factor a cubed minus b cubed. What do we get? We get a minus b times a squared plus ab plus b squared. Alright? So if we replace now a with the cube root of a and b with the cube root of b, I'm just going to make that replacement, then what do we get? We get that a minus b is equal to the cube root of a minus the cube root of b times the cube root of a squared, or a to the 2/3 if you prefer, plus the cube root of a, cube root of b, plus the cube root of b squared. Alright? So the difference of cube roots, cube root a minus cube root b, can be written as a minus b divided by all of that junk. So let's use that over here. We have to multiply and divide by this. Alright? So here, what are we going to get? This will be x to the 2/3 minus 4 times, and now we have to multiply by x to the 2/3 squared, okay, plus 4 times x to the 2/3 plus 4 squared, according to this recipe here, okay? Remember, cube root a is x to the 2/3, okay? So a in this case is x squared, and cube root b is 4. So b in this case is 64, okay? So let's erase this, give us some more room. So we're multiplying and dividing by x to the 4/3 plus x to the 2/3 times 4 plus 4 squared, okay? And we're dividing by the same thing. And if you think about it, we don't need the absolute value here, since our function is always positive and so is 4, okay? There we go. And now this stuff is going to multiply out to be x squared minus 4 cubed, so 64. Right? We get this quantity cubed minus that quantity cubed, okay? Divided by the junk that we see here, okay? X to the 4/3 plus x to the 2/3 times 4 plus 4 squared, all right? And now this is looking good because the top can factor into x minus 8 and x plus 8, and x minus 8 is what we want. So this equals x minus 8, x plus 8, divided by the junk. Now before we continue, because I really don't want to write it out again, what can the junk be replaced with? Well, x to the 2/3 is always positive. X to the 4/3 is also always positive. It's just this function squared, okay? So this business here is always greater than or equal to 0, which means 4 squared plus this business is always greater than or equal to 16, which means that 1 over all this stuff is less than or equal to 16. So we can replace the denominator with 16 and make the entire fraction bigger. Bam! All right? Now, x plus 8 needs to get replaced with something. For that, we do our stipulation, okay? So I'm going to try to squeeze it in, where should I squeeze it in? How about here? Stipulate that delta is less than or equal to, say 1 in this case, although again, really doesn't matter what you choose, okay? So if delta is less than or equal to 1, then x plus 8, which is equal to x minus 8 plus 16, triangle inequality, there we go, that's less than 17, okay? So x plus 8 is going to be less than 17, so we have at this stage, this will be less than delta times 17 over 16, okay? Now, we can let delta be now 16 over 17 times epsilon, and the proof will work, but I don't like those big numbers. I don't like 16 over 17. So, what am I going to do in this case? I'm going to notice that 17 over 16 is something that's slightly bigger than 1, so it can be replaced by a simple 2, okay? This entire thing is less than 2 times delta. And now we're going to set that equal to epsilon, so this is going to be less than or equal to 2 times epsilon over 2, which equals epsilon. The proof is done, and the delta needs to be a minimum of 1 and epsilon over 2. Why have large fractions in here if we can just have a simple epsilon over 2? Okay? All right, that's it for today. Thanks for watching.